So I'm going to, the basic problem is the fault diagnosis. And as Professor said, is to do with health monitoring. But here I will discuss not about buildings, but about gears, rotating machines, basically. But the main contributions, of course, in there, but it's looking for a greener framework, and it happens through these two things: compressive sampling and artificial intelligence. And I'll say a little bit about this um, in case you're not familiar. So this is a sort of a brief outline. So main thing that I want to say is to do with vibration signals. So our signal is vibration signal. So they're accelerometers. And I'll say a little bit about this. And then it's to do with bearing faults, but that's the particular study. And we'll use real data, and there will be some closing remarks. So the first three journal papers that we wrote on the topic, these are the first. We have written others, but these are the first three. So this, I suspect you're familiar with MSSP, Mechanical Systems and Signal Processing, and this is IEEE Access, and this is IEEE Transactions on Industrial Electronics. And they all have this, compressively sampled data and compressive sampling, and they all have that, because that is a very common thread as well as AI in this research. And we have also since written a book which is about condition monitoring with vibration signals. However, in it, we have introduced this topic, and as well as a lot in AI. So, and he was my PhD student, but he finished before pandemic. I can't remember which year, but anyway, we co-wrote this book. So what we are doing is using data, making models, and this kind of thing. So in that context, what could greener framework mean? So I'm not designing anything, I'm not building anything. So the only thing we can do is, for this greener framework, is to think about how can we reduce computation that's needed, because more computation meaning more energy use. Can we reduce data storage or transmission? Because if we have more data to transmit, it costs more in energy. If we have less data to transmit, then it's less in energy. And if we can improve accuracy, that's even better. So these are the three kinds of things that we could do towards the greener framework. And so we revisit this later on. So, and as it happens, that we'll be able to do all of these, all three. So artificial intelligence, everybody these days know what artificial intelligence is. So I say no more, except that I want to say, one way of looking at artificial intelligence and different narrative to perhaps one that you may be more familiar with is that it's an automated tool. It is a tool for a start. It's not a tool that you hold in your hand, it's a software tool. So in that sense, it's a tool, but it is an automated tool, and it can do more things. So if I have a pen, that's a tool, but it can't do very many things. I can write with it, and maybe I can press something. It's limited. But an AI tool would be able to do many more things than that. So, and also somewhat automated. But its strength is actually discovering structures. And when I say structures, it could be structure of buildings, because I'm not going to talk here, but I also work with satellite data for looking at earthquakes and where maybe there was nothing there and now buildings been built and this kind of thing. So it can discover real structure, but mainly it's about data structure. That's what I'm talking about here. And also discovering rules. So you can have engines where two people can play a game, or it doesn't have to be two, it could be more. But I'm saying like two people play a board game, and an AI can look at the game without knowing the rules, and it can discover the rules. So you got that sort of power. Yeah. And of course, the biggest bit is the application. The whole world. I've been working in AI for 30 years. And when I was first working, even my colleagues in the department, not all colleagues knew what I was doing. And now everybody in the street knows what AI is. So it's changed, and it's changed mainly because of the push that all major governments, they want to, I mean, there's a big push in China, in United States, in Europe, many, many countries. And also there's a big push around it to make money. I mean, that's why you got Meta and Google and Amazon and many others. So this is why the big push is at the moment. Now, so I come back now to compressive sampling. So we know that the way you see me is there's some light, there's some photons on my face, and it goes to your retina, and then your brain kind of makes the pattern that is me rather than it's her. That's how you distinguish. So, but the photon and the light that goes from my face to your retina is actually an analog. But your retina is actually, when we digitize, if you take a photo with your mobile camera, you're actually making a digital picture. So we're going from analog to digital. And so there is a theorem called Nike's theorem, which tells us what is the smallest sampling frequency that I can actually digitize the analog signal. And that rule is if the maximum frequency in the signal is f max, and if the sampling frequency is f sump, the Nike's theorem says that this sampling frequency must be bigger than or equal to, sorry, there should be a 2 here, twice the maximum frequency. That's what the Nike's theorem says. Twice the maximum frequency is the least. If you don't, then the signal gets messed up. So digital signal does not represent the analog signal well. So that's the Nike's theorem, and that's what we have been doing. But this century, things have changed. And it's changed that to reduce the sampling rate below the Nike's requirement, yet preserving the data integrity, this is what has happened. But it's not for all signals. So now we can sample and lower than what Nike says, and we can still actually get a good representation of the signal. Now, before I go further, which I will read out, let me say Nike's theorem is not wrong, but this is a special case. This thing is for a special case. And this is the special case, that this meaning this is only possible for sparse signal. Now, I'll explain a little bit about sparse signal in a minute. So this is a kind of signal, but the Nike's theorem is still true for all signals. He's talking about all signals, not for any special class of signal. But this is only true for a special class of signal. But the good thing for us is that this special class has an infinite number of signals. So it's not like just for 3 signals you can break Nike's theorem. There are infinitely many signals for which you can break Nike's theorem. You can actually subsample compared to Nike's rate for infinitely many signals. But these infinitely many signals must be sparse signals. Okay, so that's really been a big change for this century, early this century. And I don't give any equations because, equations, they're very important, of course, but at the same time, in a short speech like this, they take away the attention to somewhere else. I want to give you the bigger picture. But I want to say something, how is it smaller? So one way to represent this is, let's say, sample signal. So these are, each sample. So you can see long column vector, or at least this size column vector. And I'll come to this in a minute. And the idea is you end up with another column vector, which is y. So this is like, if you like, it's the sample data, but you do some things and you end up with a smaller sample, a lot less samples here than here. And the idea is that whatever we do here, Y must preserve the property of the S. If we can do that, and the answer is we can do it for sparse signal. And so how do you do that? You know, using matrix algebra, if you have a shorter thing like this from a longer thing, you have to have at least one matrix. And that one matrix must be a rectangle. It can't be a square. Because if that one matrix is square, then the size here would be same as this one. So you need now in this case, in the compressive sampling, you actually end up with only, it is one matrix if you pi times psi, but it ends up with two matrices. One is a square matrix, and this is the rectangular matrix. And you can regard the two multiplied together, these two matrices, theta, which will be a rectangular matrix. But this is and of course, to do this, it's not as simple as that. Then you have to decide and discover what the phi and psi are. And to do that, there is an optimization algorithm. And so there is a lot more mathematical details that's needed to make this effective. But that's, from conceptual point of view, that's what you're trying to do. You have a longer data sample vector, and you get to a smaller one. And by doing this operation, which is part of an optimization problem. And here, law of the time, just to give one more detail, is that the optimization problem, sometimes it uses the L2 norm, and sometimes it uses the L1 norm. But that's details, but sometimes it's important. So I'm going to show you some results. And with the two case studies, this is one, and there will be a case study two. And in this case, the data is from our own data, from our own lab. And second one will be somebody else's data. So here, if you put it as stages, so here we start at the top and we end at the bottom. And it's kind of got three stages, if you like. So this is one stage. So we have the vibration signals from the rotating machine. That's what the gear is, gearbox. And then we have the vibration signal. We compress that using this. And this is the CS, compressive sampling. So this is the stage that I described. So that's this. So this is then the reduced data set. And then this is like, so I go here. This is the AI bit, but I come back here to say you can regard this as the pre-processing for AI. One of the things is about intrinsic dimension estimation. This is a specific way of doing it. Now, the thing is when there is data, and it's almost like you want to know how many parameters you need to describe that data. And in AI terms, it's like, how many features do you need? So parameters in physics or normal language is features in AI. How many do you need? And that decides the dimension of the problem. So there is some dimensionality things you use, and this is some automatic feature selection. So this is all about, and you end up with selecting some features. So there may be many kind of parameters in the data, you collect from many things, but ultimately you need to know the relevant dimension of the problem. And that comes through, if the feature, the 10 features, then it's a 10-dimensional problem, optimization. And then this is a specific AI, is support vector machine, but of course you can replace this by another one if you want. But in this particular study, numbers I'm going to give you, it's using SVM. SVM has, one advantage. It's not to say it's better, but it has one advantage, that SVM, essentially, if you think about least square that we have learned at school, or if not school, certainly early stages in our undergraduate studies, then least square is a linear problem, So SVM is essentially a linear classifier. That's not completely true. I take a liberty, because no learning can happen without nonlinearity. So the in SBM, the optimization is linear. But the way SBM introduces nonlinearity is through what's called a kernel. So it is a nonlinear thing, but the optimization is linear. And what that means that you can use linear least square method to optimize SBM. So that's the beauty of that. For other AI things, you can't use that, which means that SBM would never be the worst performing model. It may not be the best, but it will never be the worst. Okay, and then this is some classification of the event. So this together is, we call this, so this is the right at the top, the pre-processing bit, the CS is here. And then this is the pre-processing for the AI, and that's the, we call, this describes all of this basically here. So this is the AI bit, and this is the signal processing bit. And in gear, in case you're not familiar, so a simple one would be something like this, a roller bearing, and you have, this is the inner race, and this is the outer race, and these are the balls, these are the ball bearings, and they move, but these things, they don't move, they're fixed. And so because they're the cage, so this, although this moves, this can't move too much because it can't go beyond there, and it can't go beyond there. So you can move within, roll around, and they are, of course, this is two-dimensional. They're typically spheres. Yeah. And so if you think about the problems they can have, because we're doing condition monitoring, you can have a problem that there's a problem on the outer race. There may be a break here or whatever. So when the ball touches that break, there will be vibration that you would normally expect to see. So outer race problem. There could be a problem on the inner race, meaning here there may be a problem that you can break. And again, when that ball touches that crack or whatever, then there will be extra vibration. So there is inner race, outer race. There could also be a cage fault because you got this bit that it touches, or you got this bit, it touches. So there is a cage fault, or it could just be fault on the ball itself, and so again, when the here, if there's a problem, that's not going to cause any vibration, but when it goes around to touch this, then it's going to cause vibration. So there could be a fault on the bearing, roller element itself. So what you get, the four fault condition: inner race, outer race, cage fault, and bearing fault. And there are, you'll see in a minute, there are two normal. And it sounds odd, why two normal? One is where we use completely new bearing. And so that means it's never been used, it's virgin bearing. And another set where they are no problem with the bearings, but they're used bearing, right? So we try to see if we can distinguish between just normal and new, and rather than normal and used, whether we can tell the difference. So that's the problem. And here is how many bearings there are, so there are, this is normal but used, and this is normal and new normal. And so there are 160 bearings here, 160 here, and this is the inner race fault, everything below that line, inner race fault, outer race fault, rolling element fault, and cage fault. So there are 4 fault conditions and 2 normal conditions. Sorry about this steady thing, but so there are 6 conditions. This is the 6th condition. So these 2 are normal, and these 4 are faulty. And these are just one example of a vibration signal. So when you're looking this is the amplitude of the vibration, and this is the time. So x-axis is the time, and this is the amplitude. And what you see, and this is of course only one example of it. So when you see these ones, you can see this one is very periodic. This one is also periodic, but it's a little bit muted than this one. So this one looks very different from these two. This is the inner rest fault. This one looks very different from these two. When you look at this one, that also looks very different from these two. And this is different from this one, and this one. So these two are very distinct. And these four, they are not identical or anything, but they are more similar. So one could, without, using eyes, we can tell at least there are three different classes. If we didn't have the labels, we could say these two, one class, another class, and these four, if we see, we might call them one class. So by eye, we can easily tell three classes. So I want to talk a little bit about the feature. Feature meaning when you have data and you're using neural network, you need to get a handle on the dimension of how complicated the data is. And so this is a way to try and figure out. So to begin with, we had lots of features, about 130 up to here. So this starts from 1 and 2 and all the way to here. And here is the feature weight. Feature weight, if you have used PCA, that's the principal component analysis, then for each principal components, you have a weight for them. Yeah. And bigger weight meaning that component is more important. Smaller weight meaning it's not so important. Right. And it's the same, it's not of course PCA, but similar idea. So when the small numbers, like here, it goes from 0 to 1.5 in the plot. When they're small, I mean, they're not important. And when they're 0, they're not important at all. And when they're big, I mean, they're important. So we start with something like 130. And you can already see that almost all of them, not all, a very large fraction of them are actually irrelevant to the problem. So they're not needed. And then you have to draw a line somewhere to threshold it. It could have been below here, but we chose to have it here, 0.02. And then these are the only ones left. So when we started, we had 130 dimensions. By here, we probably got 20 or whatever, I didn't count. So you can see, so that means because when you're doing optimization, it's like, if somebody tell you there's something on a line and you're looking for something along that line, then that's much easier than if I tell you it's somewhere on this. So, and of course, line is 1 dimension and this page is 2 dimension. And if it's a room, it gets even harder. So optimization gets harder and harder as dimensions increases. So it's important to get a handle on the dimension. So therefore, going from 130 to 20 or whatever, then that's a big improvement in and it's a nonlinear problem. 2 dimension is not twice as difficult as 1 dimension. 2 dimension is much harder than that. Okay, so it's important. That's why this thing is important. So here I'm going to give you some results. And the results, I'm going to take you through because, there are a lot of things I'm missing, I know, but at the same time, I want to appreciate what's going on. So first of all, I talk about this column. So this column is basically telling us how much data I'm using. And this is alpha. And remember I said about Nike's rate. So if alpha is 1, then we are at the Nike's race. And if alpha is more than 1, then we satisfy the Nike's theorem and we get more data. If alpha less than 1, we do not satisfy Nike's theorem and we use less data. And so here the idea, first of all, to say that before I give you any accuracy or anything, that all these places, we wouldn't have we wouldn't be, none of us in this world would be trying to get any accuracy at all, because it's not possible to get an accuracy, because we thought we have to follow Nike's theorem. So in all these cases, we're breaking the Nike's theorem. And here is the list, 600 samples. And here is twice as much, here 3 times as much, here 4 times as much. But still, that's less than half the Nike's rate. Okay, so that's that column. So as we go down, we are using more and more data, or as we go backwards, we are using less and less data. Then there is these 2 parameters. One is P, one is K. In a simple way, I mean, you can read those papers and you can find out, but in a simple way to say the P, this P, refers to the intrinsic estimated dimension. So, of course, we don't know the true dimension. We can only estimate these things. So we think that the data has that kind of dimension, you know, from some estimation ideas. So like when you're using this much data, that is not so much, it's about 39. And then more data, it gets more and more. And this one is in fact slightly less than that. So idea would be that this is the type of, you know, so when you have more data, as though it's getting more complicated, that's the impression it gives. And it's not that it's wrong, but K is the number of automatically selected features. So this is the number that we got from the last curve, if you like, where I showed you most of them are not needed with those red dots. So when you come here, it says actually, if we have only 14 dimensional space, 14 features, that looks good enough. And this one says 15, you know, in this case. So these 2 are similar. And also these 2 are similar, 0.3 and 4, they're similar. But these are different from these. They're about a factor of 2 different, roughly. But what is interesting now, so we're using less data and using this kind of dimension, and you see testing, classification, this also involves training, but I don't give the information of training. Testing accuracy, you're getting impressive numbers here. You're getting 98%, 99%, all of these. And what is also interesting that although this is less data, a lot less, like half the data, we're still getting pretty good results. Not as good as this one, partly from here. But so when you got a lot of data here compared to these, then you're getting this number is no different from there, but you win here, meaning it's a tighter, this is the standard deviation. So this is saying that this measurement has a slightly wider spread than this measurement. This is the tightest spread. And ideally, you'd like this to be 0, and you like that to be 100. That would be the ideal scenario. This is 100, and this is 0. Of course, real life is not like that. So this is not quite 100 and 0, but they're pretty good. And these, what happens that this is as good as this, but this is not as good as this. And that's roughly. So what is saying that not only it's doable theoretically, but this is using real data, and you're getting really good results here. Okay, I'm going to move on to, before I move on. So I'll give you some other studies. So these are references from the paper, so I don't have them here. But these are published results, and these are what I just showed you. So there is raw vibration data, and that means there is no CS, no compressive sampling used at all. And you end up getting something like this. And the compress sensing, this is some other work, using half, you're getting 92.4. And compressive sensing using quarter, so not half, so i.e. less data, then you're getting 84%. But just think about this 0.25 here. With this 0.25, when you look at these, that 0.25 sits between these 2. You know, it's more than this, less than that. And here you're already getting 99%. And here it's only 84%. It's a huge, huge difference to there. And when you have a little bit more data, you do pretty well. So what it basically shows is that you can do very well with a combination of both the CS, compressive sensing or sampling, and the AI. So this is a different data set. So this data set is not our data set. It came from US. And this is the Case Western Reserve University in US. And they have a data set they made public, and anybody in the world can use it with internet connection. And this is a similar problem, but it's different bearing and different setup. But nonetheless, one is trying to do the same thing. And this is their test rig. This one was used for collecting vibration data of bearing. So this is again real data, a slightly different data. Number of conditions are different, but similar. So here we have this bearing fault classification, and this one is the same parameter alpha. So half means we are using half the Nike's rate, half the data that Nike's rate will give. This is quarter, 0.2, 0.1. So again, all these cases, we're breaking the Nike's theorem. But here is one publication, 2015, and there one is getting this kind of accuracy. And, when it's 0.25 and 0.5, usually the feeling is that you have less data, you do less well. And that's what's happening exactly here. You use 0.25, you're getting 84%, and 3.4 standard deviation. You use twice as much data and you're getting 92%, big jump, 8% different. And this is also a lot less than here. It's 3.4 to 0.5. But here, what happens is when you use, there's a factor of 2 between them. There's also a factor of 2 between them. This is using this method I'm proposing. And then the difference is not that much. There is a tiny difference, but that's very little. And there's also, so for example, this one is only a factor of 2. Here it's a factor of 7. So for the same difference, meaning factor of 2 here, you're getting a factor of 7 difference in standard deviation. Here, for a factor of 2, you're only getting a factor of 2. So this is almost linear. This factor of 2 goes into here, factor of 2. Here, factor of 2 is 7. So it's more than the square of 2, So this is actually big. So this, by doing this configuration, we not only are using less data, much less data than even here, and you're getting much better result. These two are using less data than these and getting better results than them. So it's a surprisingly win-win situation. Another thing that I want to bring out is, remember I said about less data, and sorry, I'll go back here. So we are then using less data, and I also say it'd be good to have higher accuracy, and we are getting higher accuracy. So we tick those boxes, less data, higher accuracy. And here, I want to show you 2 things. That this is just using our framework, but although we keep the framework, but the first bit, we don't use actually the CS, but I leave it to show that it's the same framework. So if you look at the flowchart, so there is one of the boxes we take out of the flowchart, and then, So we're using all the input data. And then you're getting accuracy of 99.4 and plus minus 0.5. Here, we are using 1/10 of the data. Instead of 600, we are using 600 samples. And then we are getting the same accuracy, or you might say more, but basically the same accuracy, but standard deviation is less. So the concept, usual concept, people think less data mean less accurate and more data is more accurate. It's just not true. Because the accuracy is not to do with data alone, it's to do with the information content. So if we can actually increase the information content and reduce the data, then you can actually get better results with less data. And that's exactly what's happening here. That's the exact explanation. And the other thing, of course, because you have got less data primarily, this one, on average, it takes 65 seconds to process. And this is the variation, standard deviation. But these ones, with less data, it takes 7 seconds with a tighter variation. So you are actually using a lot less energy because that's roughly a factor of 10 energy. And so we are getting better accuracy, less data, and less time. So we succeed in doing all of those things. So we started with. So, so first of all, that we must, for this to work, we must find a sparse signal domain for successful compressive sampling. And I want to say a couple of things about it. So how is this work started for us is, so my PhD student, I asked him, what happens is, oh yeah, it's good to go back. I'm sorry, going back. Some people say you mustn't go back to previous slides, but this is breaking the rules here. Here. So if you look in the time domain, it doesn't matter which picture you take, any one of these sub-figures, it's always busy, meaning along the time domain, along time, it's always busy, There are not lots of zero samples or something. So you can't reduce. So it looks like it's busy everywhere. But so one might think this is not a sparse signal, but it's a rotating machine. And as you know, that anything that rotates, they have typical sort of frequencies. And if you have a fan, electric fan with 3 blades, or it doesn't have to be electric, it could be, aero engine or something. If you have a fan with 3 blades, you would have 3 special frequencies. Yeah. And if you have, so any rotating machine will have some regularity of that. And so, of course, noise will modulate that. Noise is not going to mind about that. So there will be some noisy signal, but there will be major frequency structure. So instead of looking in time domain, if you go into frequency domain, these signals will have very clear signatures that won't look like busy like this. In frequency domain, you only get few peaks, not so many. And that's what sparse signal is, that where everything is not busy, only some places is busy. And so I asked my PhD student then in the early days, I said, have a look at, try this and see what we get, because that's where it seems to be applicable. And that's how we really started. And of course it worked out. And so that's nice to see the theory works out. So this, then to achieve this, of course, you need the both. I'm just looking if I say that later. Okay, I'll come back to that. So the other thing is that this could be applied in any rotating machine. It doesn't have to be bearing, it could be something else, but it's got to be basically sparse signal domain. That's the main thing. And if that, we can use this again somewhere else. The other points are that it achieves accuracy that's better than using all these samples that I showed you. And that's good to have that. But of course, it requires, because it's less sample, it requires significantly reduced computation. And that's good because that's why the greener part come in. That means it needs less energy. And so we can do that. And if you think about something like wind turbines as an example, and because wind turbines are generally either onshore, but they're remote places, so it's not physically, it's not that it's not possible, but you don't go there. So wind turbines, then they send the data, they collect the data, send the data to a hub somewhere in a city, and they analyze from there. But to send the data, it costs money, it costs energy. And if you have less data, less to send, then it costs less energy. And also, even if it's offshore, then again, it's in the sea, and then it needs to send the data. And so that's useful for transmission as well. And then, of course, because of all this, so you get to save energy. And in this case, remember how I showed you that the machine learning itself is not enough, because you need the compressive sampling. So this is, as I said, without CS. That means you can switch this off. You can actually cross this out. Then it's just the machine learning bit, and this bit is identical to this bit here. So if you use only machine learning, this is what you'll get. So you get accuracy is okay, mean accuracy. This is not as tight as this, but main thing is here, you're going to use 10 times. So there is no green here. But when you combine with the CS, then you actually do far better and actually make it a greener framework. To get to the greener framework, AI is not enough. And so signal processing and machine learning are actually vital in this research. And in its way, it offers a greener framework. So I think, yeah, I'll leave it there. Thank you.